Hi, good afternoon all. Nice to see you all here. The topic for today's talk would be Introduction to Deep Learning. And for this talk we have Mr. Abel Brown, who is Senior Solutions Architect working with Nvidia. And now without much ado, I would like to hand over to Mr. Abel.
Thank you very much. Can everybody hear me in the back? Okay. All right, great. Well, it's very exciting to be here. Really appreciate everyone joining us for this talk. We're going to talk about deep learning for the next about 40 minutes or so. Then I think we'll do a Q&A, question and answer after the talk. So if you have any questions, we can talk about them. So I think probably everyone recognizes Nvidia for probably the graphics cards and the gaming. And traditionally, with the gaming, we had a huge amount of demand for computing capability, but in a very short time window to draw 60 frames or 30 frames per second for the video game. And so we had to do a tremendous amount of mathematical and floating point calculations per second to be able to keep up with the demand for gaming and high performance graphics. You can think about taking that capability to pro visualization, such as movie effects and industrial rendering. And so in the pro visualization realm, we still have all of that heavy demand for the computation and the physics engines and things like that, but we kind of don't have the demand to do it at 30 frames per second. We can sort of do it offline. And then in 2007, we decided to take all of that compute power that we had developed and make it available in a more general purpose package, and that was CUDA. And so that allowed us to do more general purpose simulations, etc., and so that really thrust us into the data center. And now today, with machine learning and deep learning, we're heavily involved with automotive. And so I think it might come as a surprise that the algorithms for doing deep learning have actually been around for quite some time. And I think since probably the late 80s, early 90s, the algorithms, the core algorithms for deep learning had actually been published. But what they didn't have at the time was enough data to train those algorithms. And probably by maybe somewhere maybe mid-2000s, early 2000s, internet companies like Walmart, Google, and Microsoft probably had enough data. But still what they didn't have was enough compute power to take those algorithms and hundreds of gigabytes or terabytes worth of data and train those algorithms. And so that was really where the GPU comes in and creates like this synergy, this big bang for machine learning, where we have the algorithms, we have the data that's needed, and also we have the compute power. And so, and this again was really enabled by opening up that compute platform with CUDA and making it more available for the general purpose, so that we could take all of that high floating point calculations per second and really start applying it to things like deep learning. So, even a few years ago, big data could be used by only probably a handful of the companies and applications, but very quickly, after just a few years, I think most markets, companies, domains, etc., probably have enough data right now to say that they're involved in big data. So even things like life sciences, law enforcement, oil and gas are now dealing with tremendous sizes of data, and it's very routine. You used to hear and think it was a really big deal to have terabytes worth of data, and now it's very common to hear people collecting terabytes worth of data every day. And so we really have, in almost every market, we have enough data to start applying these very advanced machine learning techniques like deep learning. So, and this slide is kind of more infotainment, but really just to show this real explosion of information. And so when we start to get into things like mobile web, social networks, text messages, HD video. We start really exceeding even petabytes and getting into exabyte scale. And then when we go to things like sensors, streaming video, Internet of Things, and sort of trying to make sense of all of the information streaming from these devices, we get into the zettabyte scale of information. And I think as humans, we're probably not engineered to deal with zettabytes worth of data. And so we really have to start thinking strategically about how we process and make sense of things at a zettabyte scale. And certainly, it's not getting any slower. IBM did a study and it showed that effectively about 90% of the world's data was created in the last 1 year. So we have this exponential growth of data. And so year after year, it's getting much, much bigger. So if we look at the expanding universe of modern AI, what started at these core research institutions, such as NYU and Berkeley, Toronto, Oxford, started to make all of these deep learning algorithms available through their frameworks. And so you've probably heard of things like Caffe, CNTK, TensorFlow. And so this is traditionally in the deep learning space how researchers have made their algorithms and ideas available to the community. And so these frameworks have really powered AI as a platform. And so you've got companies like Microsoft and Amazon rolling out AI as a service. And then on the other side, you've got startups, lots of startups. So many, many startups now in the AI space. And I think last year alone, there was more than $5 billion in startup funding. And so what you see is many of these AI startups being consumed actually by industry. And so industry quickly adapting and wanting to get that competitive advantage is now snatching up all of these startups and integrating those services into their offerings. So just this really healthy ecosystem of research, startups, and industry. And so if we start to say, okay, well, what is deep learning and how does it fit into the artificial intelligence space? And so very loosely, you could break up artificial intelligence into probably 3 categories: perception, reasoning, and planning. And I highlight, embolden perception, and a lot of the applications that we'll talk about over the next 30 minutes are really in that perception category. And so a subcategory of artificial intelligence would be machine learning. And traditionally, it's focused on things like optimization, minimizing a cost function, computational statistics, such as bagging and boosting. And then you've got these 2 core training techniques of supervised and unsupervised learning. And so within machine learning, you get to deep learning. And so deep learning is a neural network approach. And what is really unique for deep learning is what's called distributed representations. And so to fit data or to match objects for object detection, etc., what we use is something called distributed representation, which means that it doesn't try to make a single feature to match your data. Actually, what it does is it breaks the features of your data up into multiple representations. And not only does it do that, but it actually organizes those separate features hierarchically. And so that makes the deep learning very efficient. And sort of the thing that really puts it all together is this idea of unsupervised feature engineering. And we'll see this over and over again with many of the different examples that I've included. And the idea here is that for a lot of these examples, you don't know exactly how to describe mathematically or algorithmically what you're looking for in the data. And what deep learning really provides is this ability to do unsupervised feature engineering, where it says, I will learn from your data the features that are important to do the task that you want to achieve. And so that means that deep learning is really applicable across many different application spaces. And you as an engineer or a company do not necessarily have to know in advance the exact features that you're looking for in your data. So that makes deep learning really highly adaptable. And that unsupervised feature engineering is really at the heart of what has allowed deep learning to really grow and grow into many, many different domain spaces. So for the next few slides, we'll just go through a variety of different examples to give you a sense for really the broad applicability of deep learning, and really sort of try to excite you for the different types of applications that you can use for deep learning. So a really great example is this carbon study performed by NASA, where they have this massive satellite data set, very, very big data set. And effectively, they can't analyze every image in the data set. It's too large. And so what they have done is very quickly, within one day, they were able to train a deep learning solution to go through that data set and pick out the relevant pieces of information. And so that not only allows them to keep a much smaller data set, but it also allows them to spend 100% of their time on only the relevant portions of the information. We're starting to see deep learning take off in healthcare. This is an example from LA Children's Hospital in the pediatric unit. And the idea is that when the patient arrives, they start to take all sorts of vital signs, they have drugs administered, etc. And they'd like to predict what is the survivability for each of these patients. Can we get an early warning detection if a patient's at risk? Or can we come up with a personalized treatment plan that maximizes the survivability for this patient? And so what they've done is they've taken hundreds of thousands of medical records from patients over 5 to 10 years, and they use deep learning to build a survivability model. So they use an RNN, and so that each step of the treatment while the patient is admitted to that ICU, that intensive care unit, they can ask, what is the survivability of this patient? And they can actually predict and get early warning detection for a variety of patients. And I think they did this over a short period of time, and very quickly this model outperformed all of the mortality metrics that have been developed over 20 years. And so amazing performance for deep learning in healthcare. Another great example from Oak Ridge. They wanted to do a cancer study, and they were looking for particular patients for their study, but they didn't know how to find them. So the idea was they wanted to look through obituaries in the newspaper, and they wanted to find relevant obituaries that would identify patients for their study. And so what they did was they trained a deep learning neural network to read through basically a decade of obituaries from all the different newspapers. So hundreds of thousands of obituaries they were able to process and extract only the relevant portions of that information. And so if you think about, you as a person, if you wanted to do something like that, how might you do that? And with deep learning, they were able to do that very, very quickly and very effectively. Sort of, getting more now into some visual-based applications. And so, again, with satellite imagery, we've got this massive satellite imagery data set, many, many terabytes. And the idea is that you'd like to do a visual query through that data set. And so, in this case, it's a baseball field. And so then you want to identify all the places in this imagery where you have a baseball field. And using the hierarchical features, the way that they're organized within a deep neural network, it allows you to very quickly index through very large portions of data to find similar features. And so you can do a feature matching. And so this allows you to process very vast amounts of data to do an arbitrary, you can think of it almost as arbitrary search. Right? We know the word for baseball field, but it might be something more abstract to where you don't have a word for it. You say, just find me things in this data set that look like this thing. And so this hierarchical feature extraction really makes things like that very feasible. For the internet applications for consumers, this is an application from Pinterest. They've got millions of users, and they all like different content. And the idea is that when you like things, Pinterest suggests other things that you might like. And the idea is that it's sort of hard to write an algorithm for what people will like. And you get a collection of images of things that a consumer has liked, and it's difficult to write an algorithm for suggesting new content. So what they did was they applied deep learning that said, hey, can we just build a feature set from everything that this consumer has liked, and then suggest relevant content based on this feature map that has been developed. So they were able, in a very short period of time, I think they improved their content recommendation system by nearly 50% using a deep learning approach. And so then going to something maybe even a little bit more different, this is LettuceBot on the far right. And the idea was they wanted to reduce the cost of farming lettuce. And so what they did, and lettuce is a very liquid-intensive vegetable, and so what it does is it soaks up all the water. And so if you apply a lot of pesticides to that, it's going to soak them up. And so what they wanted to do is really reduce the amount of pesticides that they were applying for this product. And so what they did was they used cameras and a deep learning approach, and so that basically it would only spray the weeds with the pesticide instead of everything, which is the traditional approach. So not only does it really improve the health of the food, but it also improves the efficiency of raising those crops. So, kind of getting a little bit more, from the visual applications, and deep learning is even very, very effective for speech applications. So this is an example on the left here from Intelligent Voice. And the idea was that they wanted to identify at a set of audio clips, huge set of audio clips, and they wanted to figure out in each audio clip, what is the language being spoken? And this is traditionally a really hard problem. And what they did was they said, well, we want to use a deep learning approach, but I've got audio clips. And typically the deep learning approaches are image-based. So, well, how do we get an image from an audio clip? So they just did the simplest thing they could think of, which was convert the audio clip into a spectrogram. And then using the spectrogram, they fed that as an image into the deep neural network. They used GoogleNet, which is readily available, and they were able to train a deep neural network very quickly to recognize with almost 98% accuracy which language was being spoken. On the other side here we have Baidu. They're doing a massive scale language translation application with deep learning. So the idea was they wanted to translate English to Mandarin and Mandarin to English. Very difficult translation. And so using a deep learning approach, they were actually able to achieve superhuman capability with their language translation application. I think the humans they calculated were accurate to about 95 or 96%, and their language translation, deep speech, was able to achieve right around 97% accuracy. And so if you think about these applications and how you might traditionally approach solving these types of problems, typically it goes, I've got this new problem, we're going to get a bunch of subject matter experts for this particular data set. They're going to put their years and years of intellect to work, and they're going to come up with a set of features for this exact data set. And then we're going to talk with the engineers, and the engineers are going to take and write algorithms for those features, and then we're going to apply those algorithms to the data. And so this process has traditionally required a lot of expertise, and it's been a little bit slow. That process doesn't sound, the process I described doesn't sound fast. And often the feature set that's derived is brittle, in the sense that if the feature in the data doesn't exactly match, you say, oh, no, the feature's not there. And it's like, well, it was really close. And so often it can be very, very brittle. And so with deep learning, we've seen many different applications, like the speech applications, right? Required no domain expertise to be able to figure out which dialect is being spoken, right? Traditionally, you'd say, well, we need an expert in Japanese, an expert in Chinese, an expert in Spanish, and so on, and they'll derive the particular features for that language. But with deep learning, you're able to figure out which language was being spoken without really requiring a whole lot of domain expertise for that data set. And so just kind of to take this idea even further, right? And to really drive home this idea that the deep learning approach is really able to soak up the essence of the data set and really able to capture the relevant features. And so in some applications, you might take the feature set that's derived and build a search index out of it. In this application, we took the feature set and we actually used it to make a Picasso-like photo portrait. And so, if you think about what's happening here, and you say, well, what makes a Picasso a Picasso? As a person, you say, well, I know a Picasso when I see it, but I don't really know exactly how I'd describe it. And so in this case, deep learning has really soaked up the essential features of a Picasso image and allows you to manipulate those features for your particular application. And so if we take this a step further, this is a video, and we can actually apply this to sorry. So the idea is if you apply this artistic style transfer frame for frame, you get this really blotchy sort of video here. And so what they did was they took that technique and added a couple of consistency constraints from frame to frame. And what you get is a very smooth transition between the different frames. And so here this just shows a video where you're going to apply Starry Night. And so very quickly you can take and translate that whole scene into Starry Night color scheme. Just think about the different applications there for things like for video games or movies, like Pixar, right? You might be able to have a different color scheme. Your kid can pick which color scheme they like the most for their movie, or you might be able to get a whole different stylistic effect for a video game just with a simple click. And so if we start to go, and we say, so we've been really focused on this perception category, and now what we do is we take this perception, so this deep learning convolution neural network approach, it's very, very good at these perception-based tasks. And so if we start to expand out, we say, well, we'd like to combine the perception with reasoning, and we'd like to be able to take action from all of this visual input that we're able to process now using deep learning and convolution neural networks. So now using a deep learning approach, we can actually teach programs how to play video games. And they can actually get quite good at playing these video games. Of course, it's not going to let me play it again. Sorry about that. Well, at any rate, what you would see if the video would play is Atari Breakout. And the idea is that at first, it's very, very poor at playing Atari Breakout. And so it's almost a random process at first, but what it's doing is it's learning from the visual input, and it's making a map of the actions, the visual input plus the action it took, and then it's coming up with what is the optimal action to take based on my visual input. And what you see is that even after 1 hour of playing the video game, it starts to get very, very good and match human performance after 1 hour of playing Breakout. And then what you see is after about 3 hours of playing it, it's actually at expert mode. It's probably, could be just about anybody. What it figures out how to do is actually get the ball up into the top corner of the game, and so then it can just make it bounce back and forth. It doesn't actually have to take any action. It just traps the ball to where it's just running up the score the whole time, and it doesn't actually have to do anything. And so it figures all of this out on its own just by playing the game over and over and over again. And so if you think about how you would have done this even like a year or two ago without something like deep learning, writing an algorithm that could play Breakout very effectively would be really challenging. But with a deep learning approach, it makes these types of solutions very readily available. All right, so if we sort of take this this capability for taking action from visual input, really the pinnacle application for something like that right now is autonomous driving vehicles. And so if you think about sort of breaking down all the different things that you need to be able to do to effectively drive an autonomous vehicle, the very first thing that you need to be able to do, one of the core things that you need to be able to do is like recognize a stop sign. And so being able to recognize road signs is really this very first capability that you need to be able to do. Once you're able to effectively recognize road signs, the next thing that you need to be able to do is recognize the things in your field of view, like, hey, is there a car in front of me? And then be able to distinguish between cars and pedestrians. Because you might choose to do something a little bit different if there's a pedestrian in front of you rather than a car in front of you, for example. And then once you can do those two things, you need to be able to take the scene and the field of view and be able to come up with a drivable surface. And so what this is called segmentation. You need to be able to break up the image that's in view to the drivable surface. And so you can see here that it highlights in purple the drivable surface, and it highlights things like pedestrians in red, vehicles in blue, trees in green, etc. And then what you need to be able to do is be able to do these different things at different perspectives, right? You don't want just that I can recognize cars of a certain size, etc. And you might have things that are not in only partial view. And so on the bottom left here, you've got being able to do these things and recognize cars at all different scales and the depth of view here. And then what you need to be able to do is do all of these things in very poor visibility conditions like snow, rain, and fog. And so deep learning is very, very good at every one of these different tasks. And so that's really why you see that autonomous driving vehicles is really taking off, because of deep learning and our ability to do these things at very, very high accuracies. And if you think about some of the traditional accuracy of these techniques, people have been trying to do this for many years, but they've only gotten something like 85, 86, 87%, right? And you think like, well, yeah, that's really good, right? That's not bad. But the idea is that when you want to do something like autonomous driving vehicles, you really need something like 98, 99%, right? Every percent really counts in those types of applications. And similarly for medical, right? We've had machine learning in medical applications for a very long time. But when you can only get to something like 90%, that last 10% is still really critical for a lot of applications. So maybe it'll let me play this video. So the idea here is you're going to see the self-driving car basically learning to drive. So really cool. And so again, taking all of that perception-based capability and mixing it with the reasoning and planning capabilities to really be able to put everything together to make that autonomous driving vehicle. So then, you know, if we think about the demands of doing the self-driving vehicle, again, just like in gaming, there's this real hard time constraint, right? You have to be able to do these things at 30, 60 frames per second, right? Or 200 times per second when you're driving at high speeds. And so if we think about taking all of this visual processing capability and then scaling it out to where we might not have that real-time constraint, but still a very data-intensive application of all of this video processing to do things like making sense of streaming video. And so classification of streaming video has been like sort of this little grand challenge for quite a while. It takes an extreme amount of computing capability, but also it takes all of this deep learning capability of being able to make sense of all this visual input. And so, I'm trying to show this video. And so this is 90 high definition streaming video, all simultaneous at once.
Notice? So video
So this is,
being
from a recent
streamed into
GTC
that server in real time right now, and we're doing inferencing. But suppose I just want to see certain number of these. Like for example, just show me the videos that are playing instruments, musical instruments. We can instantly find them. And so imagine all of this live video is streaming through Baidu's data center. And they want to, for example, only show the Olympics or only show musical instruments and direct those videos to the audience. You can now do it completely in real time. Show me Olympic sports. Speaking of Olympic sports. Pretty amazing. All of it in real time. All of this is completely.
So, I mean, think about if you were to write an algorithm to detect playing a musical instrument. I mean, that would be incredibly difficult. Or write an algorithm to detect Olympic sports, right? It's kind of an abstract thing to be able to encode into an algorithm. And using things like deep learning, we can do this very quickly using a lot of data and then apply it to things like streaming video analytics. And so a lot of really great capability is going to come out of this. And so we're really getting to the point now with deep learning and the hardware capability that we can really do things like streaming video. And so just to summarize some of the things in all of these different examples, you know, deep learning is extremely robust. There's no need to be a domain expert in the data. You don't need to know all of the features ahead of time. It's going to learn the relevant features for the data set for the task that you're trying to achieve. And these natural variations, such as doing like the autonomous driving vehicle and things like bad weather, in fog and rain and poor visibility, the deep learning applications are extremely robust to the natural variations in the data set and can still perform extremely well, even with all of that noise that you typically come in to contact with a real data set. It's highly generalizable, so we've seen many different types of applications, but it's all just one deep learning approach. It's the same pipeline, the same design pattern, so to speak, for applying deep learning to many, many different data sets. And to boot, it's actually quite scalable. And so if you think about in a traditional machine learning problem, you've got problems of overfitting. And if you use too much data or you train for too long, typically what you can get is overfitting and your model will perform quite poorly. But because deep learning approach takes and builds this feature set, what it's actually doing is it's actually focusing on only the relevant portions of the input data. And so the more data that you have for a deep learning application, the better. The longer that you can train, the better. And so deep learning is really robust in that sense, so it's very highly scalable. And so if we take and we translate all of that for a company, for engineers, for users, right? What that means is for engineers, I don't have to be a domain expert. in the task at hand. And there's already a very thriving ecosystem, many frameworks and libraries that are already available. As a company, it allows you to quickly adapt to new user demands and new data sets and new challenges. And it's really reducing that time to insight. It allows you to take a massive data set and extract only the relevant information for your task. And so that really drives competitive advantage. And as a user, as a customer, as a consumer, really what you can expect is just better application performance, improved recommendations. I get personalized medical treatments based on my history. I get safer driving conditions from autonomous vehicles, and so on and so forth. And so there's just many, many benefits. And so this deep learning approach is really fantastic because at every level, from the people that have to make the solution work to the companies that have to support that solution and their users to the users, right? Really everybody benefits all the way up and down the food chain from these deep learning approaches. And so if we go back to ImageNet, which is a challenge where all of these things really started to take off. And so this was in 2010, 1.2 million images and 1,000 object categories. So the task was basically to write algorithms that could recognize as much content in these images as possible. And so every year they would hold this challenge. A bunch of companies and competitors would get together and run their algorithms on this data set. And so for 2010, 11, and 12, what you see is performance at right around 74%. Then in 2012, some folks applied deep learning algorithms with GPUs. And what you see is, right in 2012, you get about a 10% performance improvement. And then year after year, almost the entire competition the next year were GPU-accelerated deep learning solutions, and almost no traditional computer vision approaches. And so the two takeaways here are one, that in 2015 they achieved superhuman performance, and so they've tested how good humans are at recognizing all the content in these images. And in 2015, actually the algorithms in that competition exceeded human performance. And now you're starting to hear more and more, like Baidu, they achieved superhuman language translation. Microsoft is now achieving superhuman capabilities for speech recognition. So over and over again, you're getting to the point where you're actually superhuman capabilities using a deep learning approach. And one of the things that you see, and you'll see this in a lot of different domains, is that where traditional computer vision or machine learning algorithms were pretty much stagnant, right? 3 years, competitors really had no maximum performance benefit. But using the deep learning solution, it really unlocks that capability to provide over and over performance benefits year after year. So it's no surprise that the adoption of deep learning is really exponential. An example from Google, just the number of applications that they're working on over the last 2 years, and they're counting the number of deep learning applications that they're involved with. And so what you're seeing is exponential growth in the application of deep learning. From Nvidia, even from our own, within our own company, if you just count the number of companies that we're interacting with, specifically for deep learning, right? In just 2 years, we went from 1,500 to almost 3,500, and now in 2016, it's just a tremendous number of companies. So you've really got exponential adoption for deep learning. And so just as data is growing exponentially, we've got exponential adoption of deep learning. The thing to keep in mind here is that the model complexity for deep learning is also growing at an exponential rate. And so in 1989, this is the original network that was published, like the first convolution neural network, LeNet, from Jan LeCun. And so the idea here is that in 2012, basically it was the same network that won the ImageNet competition that really ignited all of this GPU-accelerated deep learning. And if you look at, in 2014, Google, they go from 7 layers to, it's okay, good. They go from 7 layers to 21 layers. And so if you look then the next year with Microsoft, they go from 21 layers to 152 layers. And so we're getting exponential growth in the model complexity here. And so, just over and over again, very high computational demands for really pushing these deep learning applications forward. At Nvidia, we really recognize all of the demands for training. We're building new frameworks to make deep learning applications even easier. We're releasing new hardware that's really focused on the training dimension. But also for a company, it's really important that you're able to take those trained networks and deploy them to the data center. And so we've got the DeepStream SDK for real-time streaming video processing. We've got TensorRT for optimizing trained networks to make them even faster after you've trained them. And then we've got specialized hardware that's really focused on rolling out these deep learning solutions for the data center. And just as we've got exponential growth in the demand, exponential growth in the data and the training, also what you see from the hardware side is that in just 3 years, a 65x performance improvement in the hardware for training from Nvidia. And then from the data center side to deploying those networks, you've got a 40x power efficiency improvement over the CPU using the data center products for deep learning from Nvidia. So I think in just this last few minutes, I'll talk about some of the relevant products from Nvidia for deep learning. So this is the Tesla P4. And so if you look at comparing the efficiency of a P4 with respect to even just a CPU solution, you've got about a 40x efficiency by using a P4 for deploying your deep learning solutions in the data center. And then the P40 is really focused on just sheer raw performance. And just in 1 year, you've got a 4x boost in the performance from the M40 to the P40. If you look at the P100, this is the latest and greatest NVIDIA GPU. Just so many new technologies all come together in this card, from NVLink for a high-speed interconnect for doing multi-GPU applications to 3D stacked memory, which just basically effectively means that it's really fast. And then if you've done a lot of GPU programming, you've probably hit that memory limit. And so what is really coming into play here is this page migration engine, which really alleviates a lot of that pressure for everything to fit in memory all at once. And then we've kind of consolidated all of this into what we call the DGX-1. And so inside of the DGX-1 is 8 P100s, and they're all connected by the high-speed NVLink. And what that gives you is basically a deep learning supercomputer in a box. And so for really doing the next-gen deep learning applications and doing training at lightning speed, the DGX-1 is really that solution. Let's see. And to go together with the DGX, we've got this really high-performance deep learning stack. It's all containerized, and it runs all of the major deep learning frameworks. We've highly tuned all of the containers to leverage the hardware within the DGX-1 at an optimal performance there for those containers. And so really making the DGX just this really turnkey solution for deep learning. So I'll end right here with this last slide. If you want to snap a picture, it really shows the ecosystem for deep learning and all the software components there that you can leverage for your projects. Thank you.
Actually, we are running short of the time, but maybe we can take one quick question if you want to ask. Anybody? Okay. Thank you.
Thank you very much.